Okay, so it's an honor and a pleasure to be speaking on this occasion. What I'll describe in my talk is some work of Noga, which inspired some of my own work, and then I'll describe some variations on this work that were done together with my PhD student, Roy David. Okay, so the problem that we will be concerned with is that of three coloring of graphs. So the input is a graph, and the legal output is a coloring of the vertices of the graphs by three colors, such that no edge is monochromatic. Every edge, the two endpoints have different colors. So this is a well-known NP-hard problem, hence in the worst case we do not expect to have polynomial time algorithms that can solve it. And the framework that we study here allows us to study things more related to average case complexity of this problem, in trying to understand which instances are more difficult and which instances are easier. And I'll specialize the framework here for the problem of three coloring, but similar frameworks can be done for other NP-hard problems. So the framework that we study, we call it the hosted coloring framework, and it involves two choices. One is a choice of a host graph that we shall call H, and within it, a choice of a planted three coloring that we shall call P. And the input graph G to our problem is obtained by starting from the host graph, planting in it a three coloring P, and then removing those edges that are monochromatic under this three coloring so that the graph is really three colorable. So let me just, to make sure that we understand the model, so we start from an arbitrary host graph H. Then we plant in it some arbitrary three coloring P. It does not need to be a legal three coloring. It can be, so for example, here there are some monochromatic edges, which I marked by red here. So now we modify the graph so that the coloring becomes legal. So to modify the graph, we need to remove those violating edges. So now we get a new graph. From this new graph, we remove the colors. We no longer see the colors, and this is the input to our problem. Now we get this graph as input, and we need to color it. So the algorithmic challenge is as follows. The input is the graph G, and the algorithm never sees the original graph H, the host graph H, or the planted coloring P. And the goal is to find a three coloring of this graph G and do so in polynomial time. And we don't insist on finding the planted coloring, the original planted coloring. Any three coloring that you find, as long as it's a legal three coloring, is okay. So this is the problem that we're going to study here. Now, this is the general framework that we study. Within this framework, there are several different models. So a model specifies how we choose the host graph H and how we choose the planted coloring P. And the difficulty of the problem depends on the particular model that we will be looking at. As an extreme example, if an adversary who's out there to make life difficult for us is the one who chooses both the host graph H and the planted coloring P, then we can get arbitrary graphs, three colorable graphs, and since three coloring is NP-hard, we don't expect to have a polynomial time algorithm for coloring them, because then P would be equal to NP. So at the extreme end, we have the very difficult problems. A special case of this model, it wasn't presented in exactly the same form, but this is a well-known model. You can call it the block stochastic model for coloring, is when the host graph H is just a random Erdős-Renyi graph, and the planted three coloring is also just random. So this is the same. This model was introduced by Kuchera already long ago. And another way of looking at it, you have like three color classes. Each of them is an independent set. And between the color classes, you put just edges at random with probability P. For us, it would be more convenient when we talk about random graphs to parameterize them by their average degree d rather than by the edge probability p. So I'll use the notation GND instead of GNP to denote this. And since we're dealing with recoloring, our model can be called, this particular model can be called GND3 because there are 3 color classes. So to get some intuition, let's see some simple algorithms in this model. So suppose now that we have very large degree in this model. Think of degree larger than, let's say, square root n. What would we do then? So we can observe that if we have 2 vertices who are at the same color class, let's say in the red color class, then potentially they have neighbors both in the green color class and in the blue color class. So there are 2 other color classes in which they can have neighbors, common neighbors. Whereas if we have 2 vertices in different color classes, there's only 1 color class in which they can have common neighbors. So we expect them to have fewer common neighbors. So if we just count for every pair of vertices their number of common neighbors, this should tell us whether they're in the same color class or not. So we set a certain threshold, and if the number of common neighbors is above this threshold, we say they're of the same class, and below the threshold, they're at different classes. And this actually works when the degree is large enough. When the degree is significantly above square root n, then vertices are expected really to have common neighbors, and these counts work out well, and we can recover the actual planted coloring. Can we do better than that? Okay, so there was work of Avram Blum and Joel Spencer that did better than that. It could find the planted 3 coloring when the degree, it did not have to be larger than square root n. It was enough that it was n to the epsilon for any epsilon. And the idea is rather than counting common neighbors, at these degrees, 2 vertices are not expected to have any common neighbor whatsoever, so common neighbors don't help us. You look at neighborhoods at larger and larger distance and compute statistics on them. And if you do it right, you see that if 2 vertices are from the same color class, the statistics look different than when they are from different color classes. And using this idea, they could 3-color these graphs as well. Okay, so now we get to the main topic of the talk. So this is work of Alon and Kahala from, this is the journal version, the conference version was earlier. And they proved, I'll separate the results into 2. So the first result is the following, that a spectral algorithm that uses eigenvalues of graphs can find the planted 3 coloring whenever the degree now is much smaller. It's just a constant times log n. So even at that density, we can find the planted 3 coloring. And the second theorem says that even at smaller values of d, we can actually, let's say, constant average degree, you can still find a 3 coloring. At this point, you cannot find the planted 3 coloring because it's no longer the unique 3 coloring of the graph. There are many different 3 colorings of the graph, and you can find one of them. And this is quite a significant achievement because in many settings, once the planted solution is not the unique solution, it becomes much more difficult to find it, and here we can actually, to find a solution, and here we can actually find a solution. So all the results hold with high probability over the choice of, it should be the host graph H and the random planted coloring P. So, of course, they cannot guarantee success on every graph because the problem is NP hard, but for random graphs at these densities, it works well. So what do we want to do? So what the topic of this talk here would be what aspects of randomness are needed for this result of Alon and Kahala. So for example, did we really need the host graph to be random, or is it okay if it's just an arbitrary expander chosen by the adversary? Likewise, do we need the planted coloring to be random, or can an adversary choose it after seeing the host graph and then choose his own planted coloring? Would the results stay the same or change under this change in the model? So as an outline of the talk, first I'll review this algorithm of Alon and Kahala in a high level without detailed proofs. Then first we'll consider what changes when the host graph is an expander chosen by an adversary instead of a random graph. Then we'll consider what changes when the planted coloring is adversarial instead of being random. And then we'll end with some open questions. For what? Like what's the best constant for which the algorithm works? I don't think it's known. No. But it goes below the, the reconstruction, The coloring is no longer unique. Usually people ask what's the threshold at which the planted solution is the only solution, where you can do exact recovery. This goes much below it. So.
Is it a small constant?
I think they also ran experiments, so maybe Noga can say what they found out. But
it's not very small, so it's probably 100.
Yeah, okay. So, okay. So to understand the results better, it's good to describe different notions of colorings of a graph. So let P is the planted coloring. I already introduced it. Now, it would be some of the algorithms, as a partial result, achieve what we call an approximate coloring, or a B-approximate coloring. So this is not necessarily a legal coloring of the graph, but most of the vertices are colored exactly as in the planted coloring. So it's something close in Hamming distance to the planted coloring. You made some progress, but you did not yet color the graph. The next object is what I will call a safe B partial coloring. So this is part of the graph is colored, part of the graph is not colored. The part which is colored exactly as in the planted coloring, and the part that is not colored yet, you need to color it. So this is a much better situation to be in than in approximate coloring, because you know when you are right. You know which vertices are colored correctly. And then what we seek to find is a legal coloring, so that's any legal coloring of the graph, not necessarily the planted one. Okay, so to understand also the performance of the algorithm, it's good to distinguish between good and bad vertices. So this is, you start with a host graph, and you planted in it a coloring. So we say a vertex is good if it has the 1/3 of its neighbors in each of the color classes. And after we remove the monochromatic edges, so half of its neighbors in each of the other color classes. So that's a good vertex. Its statistics are the way you expect them to be. And a bad vertex is one that does not obey it. And if we look at a random planted coloring, so it's not difficult to show that the fraction of bad vertices is going to be pretty small, so exponentially small in D. In particular, if D is larger than log n, we don't expect there to be any bad vertex. All vertices would be good in terms of the statistics that they see, how many neighbors they have of each color, it's roughly the same. Okay, so now that we have this preliminary part after us, so let's see the main steps of the algorithm of Alon and Kahala, and later I'll give a few more details. So the first step is a spectral algorithm. You do some sort of spectral clustering. What it gives you is an approximate coloring. So most of the vertices you actually color correctly, but some fraction of them, something like n over d, you don't color like the planted coloring. So among them, you might have edges that are monochromatic. The next step is some local improvement to reduce the fraction of vertices which are not colored like the planted coloring. So there's some local improvement step. And this by itself already, if the degree is larger than log n, in fact recovers the planted coloring, because the fraction of vertices which are not colored according to the planted coloring is only like this parameter b, the number of bad vertices, and if the degree is larger than log n, there are no bad vertices. But if the degree is constant, you need to work further. So now there's what I view as a very clever step So this goes from an approximate coloring to what I call a partial coloring. You uncolor some of the vertices, and you get the guarantee that most of the vertices do remain colored, and they're colored exactly as in the planted coloring, and only the uncolored vertices are those that you need to now color. And when you reach this stage, on the rest of the graph that remains, you run some other simple coloring algorithm, let me call it here dynamic programming, and it completes it to a legal coloring. So these are the main steps of the algorithm of Alon and Kahala. And so let me give a few more details. So for the first step of the algorithm, the spectral part, you need a little bit of a spectral graph theory background, not much. So if we look at the adjacency matrix of the graph, there are the eigenvalues, lambda 1 up to lambda n, which lambda 1 is the largest. And it's known that for a random D regular graph, lambda 1 would be roughly D. And the most negative eigenvalue would be roughly minus square root of D. So it would not be linear in D. Whereas once you plant the coloring, any three-colorable graph which is roughly regular does have very negative eigenvalues, which are, once you planted the coloring, the average degree went down to 2D over 3, and you will have eigenvalues which are minus D over 3, you will have two of them. So this is some background in spectral graph theory. So how do we use it in the algorithm? So the host graph, we said, was the random graph. In it, we planted the random coloring. And then now we want to start our coloring algorithm. So we'll compute the eigenvectors that correspond to the two most negative eigenvalues. They came from the coloring in some sense. So they contain information about what the coloring is. So for every vertex, you can look at its as its value in each of the eigenvalues as its value in some coordinate system. So it's like a mapping of the vertices to the two-dimensional plane. And you do some clustering algorithm in the two-dimensional plane, and it gives you a pretty good coloring. I will not give more details than this. At the time this work was done, these ideas were pretty new. I mean, very few papers used ideas of this sort. By now, this is standard. I mean, everybody who works on planted models knows how to do this stuff. Or not everybody, but a lot of people. Okay. Okay. So let's see the picture after this first step. So the whole green blob, I look at it as like the whole graph. And most of the graph is colored in green. So it's the color that we associate with the vertices is exactly as in the planted coloring. And there are some regions in the graph where this is not so. These are the red parts in the graph. Okay. The next step is a local improvement step. In this step, what we do, you take any vertex, looks locally, and says, do I think that I'm in the right color? So what does it do? It counts how many neighbors it has in its own color and in different colors. And if it has many neighbors in its own color and a smaller number of neighbors in a different color, it would like to switch color. So it would be involved in fewer violating edges. So that's a natural step to do, and you do it. And after you do it, the theorem says that your coloring improved. So if before this was the picture, after you do this local improvement step, the bad regions become much smaller. Okay? And they completely disappear if the average degree is above log n. In this third step, you do some uncoloring. Okay, so in this, if you have a vertex that suspects that maybe something is fishy about his neighborhood, let's say he sees too few neighbors of other color classes, it just uncolors himself, becomes uncolored completely. So if you do this iteratively, then what you get is the following. You started from this situation, and all the bad vertices, those which were not colored according to the planted coloring, it turns out that they uncolored themselves. They are no longer colored at all, and also some of the good vertices may be uncolored themselves. But we have so now we're in the situation that most of the graph is colored exactly as in the planted coloring, and a few vertices are uncolored, but we know that there's a way of completing the coloring because so far we made no mistake whatsoever compared to the planted coloring. And the last step is this: how to finish, how to color what remains. So you want to say that the part of the graph which remains is easy to color. And as some intuition, because it's very small, if these were just random vertices that remained uncolored, they would not form any large connected component. And the theorem says that, in fact, even though they are not really random, the graph we started with was random, and the planted coloring was random, but then we ran an algorithm, only did a lot of stuff, so by now we used our randomness. But still it's true that the parts that remain don't make any large connected components, and each connected component you can color by itself using exhaustive search, because it's small. So you can, in polynomial time, color arbitrary components of size log n. Okay. So we started this stage with this safe partial coloring and ended it with a legal coloring, and here the new vertices I gave there a different shade of green because this is a legal coloring, but they are not necessarily colored the same as the planted coloring. They may have be colored differently, but it is a legal coloring. Okay. So this is a summary of the Lowen-Kahala algorithm. It had these 4 steps. And now let's move to what we want to do. Because it's not an exhaustive search over everything simultaneously. You do it one part, finish it off, do another part, finish it off, do another part. It's not the total number of vertices which are not colored is linear, in a sense, could be. So you cannot really run it as exhaustive search. Okay. So now what do we want to do? We want to ask ourselves, does the host graph need to be random? So if we look what the analysis used, I didn't show what the analysis used. But one part was the eigenvectors, eigenvalues of the graph. And the other steps also implicitly use something related to eigenvalues of the graph, because the other steps of the algorithm use the expansion properties of the graph, and it's known that expansion is strongly related to eigenvalues of the graph. So we can ask, let's say that we have an arbitrary now host graph for which all that we know is that the second largest in absolute value eigenvalue has value much smaller than d, much smaller than the largest eigenvalue, so it's a good expander. Would the whole algorithm work then? Or it could be max, okay. Up to a change of sign, and, yeah, okay. Okay.
H is assumed to be regular?
So no, you can think of H as roughly regular. It doesn't have to be exactly regular, but for simplicity, let's think of H as a regular expander. But the adversary can choose the expander. So how does our algorithm look like? So it's the same algorithm. And the question is, does it work? And okay, so we use essentially the same major steps of the algorithm of Lowen-Kahala, but the details of how these steps are implemented are a bit different in some places. And the main difference is really in the analysis, which has to be work. First, there's no randomness in the host graph. All you're allowed to use is expansion and randomness of the planted coloring. And even we don't assume that it's a very good expander. So the second eigenvalue does not have to be something like square root of d. It's enough that it's a constant times d, and our analysis works. So let me point out one difference. So there are many small differences, you can say, between our algorithm and the one of Lowen-Kahala. So let me point out one point where we differ, just briefly describe it. So recall that we had these situations where we had this safe partial coloring and we needed to complete it to a legal coloring. And for that, we needed this theorem that I glossed over, but it's not so easy to prove it. That with high probability, those random regions which are not colored yet form only small connected components. This is not so easy to prove. In my opinion, maybe it's the most complicated part in the paper of Lowen-Kahala. Others may think differently. So it's not so difficult to prove, not so easy to prove, but of course, for some people, maybe it's easier than for others. And what we do something a bit different, so we circumvent the need to prove it and do something a bit different, which is very natural, but somehow was not observed before. So what we say, even if the connected components of three vertices are arbitrarily large, I don't care, those which are not yet colored, we can still complete the partial coloring to a legal one, as long as the number of uncolored vertices that we start with is not large. I don't care about the structure. And this is by the following simple rule, we can call it safe recoloring. Whenever a vertex sees among its neighborhood already two colors, he knows what its color has to be, because so far the coloring is consistent with a blended coloring. So if I'm not colored and I have a blue neighbor and a red neighbor, I know I have to be green. Okay? So you just do these steps. So that's something very natural. But the nice thing about it is that once you do it, everything becomes simple, relatively simple. So when you no longer can do this step, then you can show that the connected components that remain of uncolored vertices are small, smaller than log n, and some factor that depends on the expansion. And the proof of this does not need to use the randomness of the host graph. All it uses is just the randomness of the blended coloring. And in fact, if we start with a very strong expander, like a random graph would be a very strong expander, a host graph, then the proof is actually very simple, just a union bound. And the more challenging thing is to prove it also when the host graph is just a mild expander. When the second eigenvalue is a constant times d. This is a more clever proof, but we can still do it. Yeah.
But you need to blanket these random, or it's
Yes.
every color appears roughly the same number of times?
No, we'll get to that. We need that it's random. This is something we'll get to.
How much is from 3 color? Do you want to do it for K coloring?
Yeah, everything I say we can generalize to K coloring. Just for simplicity, I'm talking about 3 coloring. Yeah, there's one small thing I'll mention it which doesn't hold for K coloring, but we did not get to it yet. So now the second question that we ask ourselves is now, does the blended coloring need to be random? So, or the alternative thing is that you see the host graph, the adversary examines this host graph, picks very carefully which vertex gets which color. As long as the 3 color classes are balanced, he's allowed to choose any blended coloring. Now can we color it? Does this matter? So here there's a difference between what I said before with the issue of good and bad vertices. Before, when the degree was above log n, we said there are no bad vertices. Each vertex sees roughly the same number of neighbors of each color class. Once the adversary picks the coloring, this is no longer true. Most of the vertices would be good in the sense that they see roughly the same number of vertices of each color classes, but now this is a consequence of expansion. You need to say something about the host graph for this to hold. If the host graph is an expander, this would hold. Okay, you need expansion, and the fraction of bad vertices here is much higher than before. So it's something like, okay, even if, let's say, if lambda is a constant times n, it can be linear in n even. Even if lambda is a constant times d, it can be even linear in n, regardless of the degree, for example. Whereas in the case that the host graph, the blended coloring is random, the number was much smaller. So now if we return to our algorithm, the Alon-Kahala algorithm, and see what happens. So we start with the spectral coloring, and when you do the analysis, you can do the analysis, it gives you bounds which are, it gives you an approximate coloring, maybe not as good as when the blended coloring was random, but still pretty good. And then when you do the local improvement step, you improve it, not as much as you did when the blended coloring was random, but you still improve it. And when you do the cautious uncoloring, you can still get that most of the graph, you know exactly the coloring, the blended coloring of its vertices, and you remain with a small part of the graph for which you don't know the color. And then you need to finish off by dynamic programming. So what's the running time of the algorithm? So the first 3 steps takes polynomial time as before, and the only question is how long does the last step, the dynamic programming, take at the end? So the situation, we know exactly the color of almost all vertices in the graph. A small fraction of vertices are still uncolored. Can we just complete this coloring? We already did almost all the work, 90% of the work, only 10% remains. Can we do it? And the answer is, okay, no. So if the host graph is an adversarial deregular lambda expander, and the planted balance coloring is adversarial but balanced, then 3-coloring the resulting graph is NP-hard. We can find and almost color everything, but we cannot actually 3-color it. This holds for essentially a very wide range of degrees, so it doesn't matter, the degrees can almost be linear and it's still true. And even if the host graph is a wonderful expander, it doesn't really matter. Okay, so the result holds. So in other words, okay, it's easy to find a safe partial coloring that colors almost everything correctly, but then to complete the coloring becomes difficult. So let me sketch how the proof goes. So suppose we had an algorithm that can 3-color graphs G generated in these models, that you start with a spectral expander, an adversary plants in it a planted coloring. Then let's take some small sparse graph which is, let's say, NP-hard to 3-color, because 3-coloring is NP-hard, and give our algorithm this small graph and ask it to color it. So the claim is it will color it. That's what we want to say. And hence, it solves an NP-hard problem, and hence, there's no such algorithm. But the question is, why would it color it? It doesn't seem to come from the right distribution of graphs. So we need to change Q a little to fool the algorithm into coloring it. So how do we change it? So what we do here, Q, this is our small NP-hard graph. We append next to it a very large expander. Okay, so you can think of it just as a random graph, a very large expander. And now, in this expander, we ourselves plant a planted 3-coloring. This we can do. Okay, we just at random partition it into 3-color classes and drop all the edges between them. So we planted it in a random 3-coloring. And now we give this as input to our algorithm and ask it to 3-color this graph for us. Okay? So now if the algorithm indeed colors this graph for us, it also colored Q for us, which was an NP-hard problem, so we don't expect this to happen. But why do we expect the algorithm to succeed on this graph? I'm saying this graph looks exactly like a graph that can be generated from a spectral expander H and a balanced 3-coloring P. There's another way of generating the same graph that I described, which is within our model. And so how does it work? This was our graph. How do we see that it's really composed of an expander in which we planted a 3-coloring? So let's work backwards. So first, this Q was 3-colorable. We don't know what the true 3-coloring is, but an exponential time adversary would know. So there is some 3-coloring of it. We can add edges now between color classes, just between the same color classes, in Q and in Z. And then we can drop the edges, we can put back the edges that we dropped from Z because of the planted coloring. So now this would be our graph H that we started with. So one claim is that this is indeed an expander, which is not so difficult to prove. And the other is once you planted it in a 3-coloring, this one, and you drop the monochromatic edges, you get exactly the graph that we gave as input to our algorithm. So to complete this NP hardness proof, so we say that if Z, this expander, is much larger than the Q, the graph that we try to color, then H that we constructed as above is indeed an expander. This needs a proof, not so difficult. And that the graph G that we derive from an expander with the planted coloring looks exactly the same like the graph that once we had Q, we gave it to our algorithm and asked him to color it. So if the algorithm could color G, it could solve NP-hard problems, and P would be equal to NP. Okay. So now we get to the main hardness results. Looks the same as this one, but considerably more difficult, which is the following, that if the host graph H is a random graph now, it's not an expander that the adversary chooses. It's a random graph that the adversary has no control over whatsoever. And now the adversary, all he can do is plant the 3 coloring in this graph. Then 3 coloring the resulting graph is also NP-hard. Okay? So even this is NP-hard.
So this is for D which is large constant.
So for what value of D does this hold? So this is quite interesting. We could prove it only for some range of degrees, which is somewhat below square root n. If the degree is much higher than square root n, we know that the theorem is just not true. And if it's much lower than small square root n, we don't know. Okay. So something strange is happening here. So the hardness result somehow would need also the random graph H to have large degree, but not too large. And maybe I should emphasize here, so people who are familiar maybe with NP-hardness results maybe are aware of the fact that there are no NP-hardness results whatsoever for random objects. So when you look at random models, there are no NP-hardness results. Some problems associated with random objects are difficult, but we don't know to prove that they are NP-hard. So here, this is not a completely random object. Here we have a mixture of randomness, which for the host graph, and some adversarial choice. Doesn't look like a lot of adversarial choice here, but that's enough to prove NP-hardness. So I just want to emphasize that this is somewhat non-standard, the fact that you can prove here NP-hardness. So how would the NP-hardness result look like? So what would we give our algorithm that can color in this model? So as before, so this is, we take some small graph, which is hard to 3-color Q, and append next to it. This time you can take a random graph and planted it in a random 3-coloring, and this is the input graph G for which you ask your algorithm to color it. Okay? And now we want to claim the algorithm would color it for you. So why is this so? So we do as before. We say, okay, think of this graph as being derived from something else, which is something like this. So you found the 3-coloring of Q, added edges, and so on. But now the question is this, so this is the graph H that the adversary could start with, and after planting the coloring, get our graph. But the question is this a random graph at all? Because the adversary has no control with what he starts with. He just gets a random graph, that's his starting point. Why would this be a random graph? Okay, so that's the difficulty in the proof. And in fact, in some cases, it's not a random graph. So for example, if the degree is too large, okay, so maybe let me go back to the picture. If the degree is too large, one property that we needed here is that if we look at vertices here and vertices here, they don't have common neighbors here. This is part of what our reduction does. If they do have common neighbors here, the reduction breaks down. And if the degree is larger than square root n, they will have common neighbors here. So the reduction would not work. So in fact, it's not really the issue of our reduction not working. In fact, if the degree is large, it's larger than n to the 2/3, we actually have an algorithm that colors graphs in this model where you start from a random graph and plan an adversary plants in it 3-coloring. We can actually color them in polynomial time. So there's a real reason why this reduction cannot work at high degrees. Another aspect is that the host cannot have a degree which is too small. And this is maybe a bit more delicate why this is true. So we want our subgraph Q, the NP-hard graph Q, to be a subgraph to occur naturally as a subgraph of a random graph. We cannot plant it in there because the adversary has no control about the initial host graph. It's just a random graph. And if the degree is too small, then just you would not get your graph as a subgraph of that graph, because just if you just do the computations, maybe I will not do them here, it would not happen. So in fact, based on this, we have to be very careful on how we choose the NP-hard graph Q. It has to be of average degree between 3 and 4, it has to be like that, and it has to be balanced in the sense that no subgraph of it has larger average degree than the whole graph. So it has to have average degree strictly smaller than 4, strictly larger than 3, and to be balanced. So we need to prove that on these families of graphs, 3 coloring is NP-hard, so we do that. And then the proof can start working. So I'll not give more details, just like the main lemma is the following, that the graph G, this is what we give to the algorithm, which is a disjoint union of this small balanced graph Q of average degree 3.75. This is from a family of graphs which is NP-hard to color. If you append next to it a random graph in which you planted the 3 coloring, and this is your input graph, this is statistically indistinguishable. It's not exactly the same distribution, but close in, let's say, L1 distance, to a graph G that you can get from starting from a random graph and planting, and have an adversary very carefully plant in it 3 coloring P. So these 2 distributions look the same. So this is like the main statement here, and this requires a proof. I mean, it's not trivial. No. So 3.75 is just the simplest construction that we had, but you can do it. We know how to do it for slightly smaller degrees as well. And it's open how low you can get, in fact. Yes?
How big does zinc brine have to be?
So think of, we know that we can find this partial coloring in which the fraction of vertices which are not colored, all the rest are colored, is something like n over d. So the fraction q, the size of q relative to the whole graph, it can be roughly 1 over the total degree, not more than that. So it has to be much larger, this z-prime. Okay, so let me summarize. So what we were looking at is the following framework. So we have a host graph and a planted coloring. And the host graph can either be random, or an adversary can choose it, but it has to be an expander. And the planted coloring can either be random, or an adversary can choose it, but it has to be balanced. And previous result only addressed this region of random host graph and random planted coloring, and managed to design algorithms for it. So what happens in our cases? So if we look just at approximate coloring, just this is our goal, to find an approximate coloring. Most of the vertices are colored correctly. Then the spectral algorithms work for all of them, sometimes with somewhat different parameters, but basically work for all of them. If we look at the additional combinatorial techniques that were added later to get a partial coloring, which is part of the cleverness of this Alon-Kahala algorithm, so also they work for all of them. So it's also you can get a partial coloring in for all of them. And the main differences come when we want to find a legal coloring that colors everything correctly. And here the picture is much more interesting. So somewhat, at the beginning it may have looked trivial, I don't know, that when the host graph is an adversarial expander and not just random, the algorithm works. But seeing that here it does not always work, maybe this also was not so trivial. Okay, you needed to do some work here. As we said, if we have an adversarial expander and adversarial balanced planted coloring, it's NP-hard, essentially for all degrees. And this is really the most interesting region, where the graph is random, the host graph, the planted coloring is adversarial. Here, when the degrees are very high, above n to the 2/3, we can color it in polynomial time. If they are below, let's say, n to the, let's say, below square root n, somewhat below, it becomes NP-hard. There are some regions that we don't know what exactly happens. And I should mention about when we look at K coloring, the picture looks the same. The only difference is that this disappears. This is special for 3 coloring. That at high degrees, if you have a random graph and an adversarial planted coloring, you can find it. That's no longer true when you go to k coloring for k larger than 3. Other than that, it's the same picture. So now let's just finish with open questions. So the open questions are there polynomial time 3 coloring algorithms for the following settings? So one of them we've seen. So the host graph H is a random graph, but now the degree is below the region where we can prove NP hardness. So let's say take it as n to the 1/4. Okay, at this region our proof breaks down. And the planted 3 coloring is adversarial. The question is there a polynomial time algorithm for coloring it? Yes or no? So that's one open question that I think is very interesting. So the next open question relates more to our general framework. We said we have many models in our framework, not just the random planted model. We have other versions. So here's a question about a different model within our framework, which I think is also an excellent question. So here the host graph can be arbitrary. The adversary can choose any host graph that he wants. Doesn't matter what, no restrictions whatsoever. And in it you plant a random 3 coloring. Can you find a 3 coloring of this graph? Is this easy or hard? We don't know the answer to this. We know in special cases, if he happens to choose a host graph where the minimum degree is very, very high, let's say linear in n, then you can color the graph after you plant the coloring in it. That's not so difficult. But in general, this question is wide open. Okay, so I'll end here.